Alright, welcome to episode 22. I'm having a lot of fun with this keyword optimization stuff for some reason. I think it's just because I've never had a chance to play with hash tables at this level of detail before. But it turns out your choice of a hash function it can make wild differences in the number of collisions you get, and randomly changing it in a really small way leads to finding optimizations really easily. So that's kind of cool. So you can just try 100 random seeds and figure out which one gives you the best result, and if it's not good enough, go to the next table size up and try it again, and it optimizes pretty cool in a pretty clean way. Like in a pretty easy to implement way, you just find tables where you minimize the error and you don't have to make it very big at all, and it's really cool. So what we're going to do now is robinhooding. We're going to try to get our max single error score down closer to 1. So if I just first of all get a sample of, right now I'm not doing super heavy optimization, but like in the lightweight optimization case, using light optimization effort, I end up needing about 10 extra slots to get an error score that is less than 1 error per slot, per used slot, and my max single error tends to be around 10. Sometimes I get really good ones where it's like my max single error is 4 or 5 or 6. But yeah, I think like 8, 7, 10, 11, 12 shows up fairly often too. Definitely more often than anything below 6 or even at 6. So we want to try to drive this number down without pessimizing any of those. And the way to do that, and pessimizing those as in, this would obviously not be pessimized, but we don't want to have larger tables come out as a result. And the way to do that is going to be robinhooding. But before we do any robinhooding, I want to do one other quick sanity check. What happens if I put in a heavy optimization effort? Is this still pretty bad? So heavy optimization effort takes a little bit more time to run, and it goes for smaller tables, but it looks like it actually does just as bad on this front right now, which makes sense. In fact, it might even do worse, which I only say because I saw a 13 for the first time. Sometimes it gets 6s, so it's also capable of getting lucky, but it seems kind of like it's about as bad as the other one. Yeah. Yep. Okay. So they're about the same. Let's try and improve the light optimization effort case first, just because that lets us run more quickly. And hopefully the optimizations that give us smaller numbers here will give us smaller numbers for the heavy optimization case too. They should, because robinhooding only decreases this. It, at the very least, does not increase this. So here's how we do robinhooding. When we're in here and we see that we have an empty slot, we still insert and we have the same contributed error as we had before. But the idea is that when we are looking at a slot that is not one we can go into, we might trade responsibilities. We might say, hey, I want to take this slot and make you keep moving, but the reason I want to do that is because the contributed error numbers will change then. So how the contributed error gets added into the total error needs to be more carefully computed, and how the contributed error, like max, gets computed needs to be more careful. But I'm going to ignore those problems for now and just look at getting the basic swapping of robinhooding in there correctly. So in order to do robinhooding, what I have to do is say, look, if the spot I'm looking at is already taken, but it's in my sequence, so I've already done my hash and I'm linear probing along, if the spot I'm looking at is taken, I want to then look and say, hey, I know my contributed error and you know your contributed error, so let's see if it would be better for you to keep moving down and me to take this spot, right? And by better, what we mean is minimizes maximum single contributed error. Whoever, if me taking this spot and you increase, and the person already in this spot growing their particular error is better, then they should do that. And it's better when, or rather, the time when them growing their contributed error does not increase the maximum occurs when my error is already bigger than theirs, right? So if my contributed error is greater than the layout.contributed error index, that means my error is already so big that if I keep going down, I could be starting to raise the contributed error total. If you moved down, you would at least in the next step, maybe one step over, you would perhaps after one step over, you're going to start increasing the contributed error. But there's a chance that for at least one step of this iteration, you won't be, and that means that the total you reach will be one less than the total I reach, right? Another way to put it is, if our contributed errors are the same, then that means we both wanted the same slot to begin with, and which one of us continues won't matter. But if your contributed error so far is smaller than my contributed error so far, that means that I started farther away than you did when we both got here, which means I should take this spot and you should keep going, because then your distance from your spot will still be less than my distance from my spot would have been, right? And therefore our maximum distance from everyone's home location, the first spot they checked, shrinks, because everyone is applying this logic. Okay, so my contributed error is greater than your contributed error. Then what's going to happen is we're going to say, first of all, we're going to need to keep track of which error keyword we're trying to insert. And so the keyword we're iterating up there doesn't want to get affected, but the keyword insert does get affected. So the keyword we're trying to insert becomes the keyword that's at the layout slot already. Right? The contributed error that I already have needs to get dropped into here at this time. So whenever I'm inserting myself in, that's when I should do this. So the layout.slots index should become prev keyword insert. Right, so we're kind of swapping. Right. So here's the keyword insert we were doing. Save that here. Change the keyword insert we're going to do to the one that's in the slot we're swapping with. Then the slot we're swapping with gets the old one. Right? Standard swap pattern. In fact, we could just write this as swap keyword, swap the keyword insert with layout slot. There we go. Perfect. So I've swapped that in. Now the keyword insert is whatever used to be in that slot, and the slot contains whatever the keyword insert used to be. Great. While we're at it, we also want to swap the contributed errors. Essentially, my contributed error needs to get written out, and the contributed error, right, so this is eventually going to work out to be a swap, but I want to see it all written out first, and then I'll condense it down to a swap. So the previous contributed error, the contributed error changes to whatever was in here, which means we're guaranteeing that this number just became smaller. And then we want to say, hey, so my contributed error ended up being this, right? So I took that slot, and we just need to register that this could be the new contributed error max, because I just went into the table and this was my contributed error. So this could be the new max, right? Another thing we kind of want to do is we want to increment our error score at this point here, and then we want to say when this happens, increment by the thing we just inserted, but then decrement by the thing we pulled out. And so this is why I didn't end up actually manually doing the auto swap, because I kind of suspected we were going to want these pieces of information here. But what we can do is we can still turn this into a swap if we change the order when we do them. And that's going to make the code make a little more sense in my head. So what's actually happening here is that the contributed error is going in, as it does up here. So we're going to say that this actually happens as a first thing before the insert. Before we insert anything into this table, the max single error score is based on whatever thing we're inserting in now, its contributed error. And the other thing that happens is we add in the contributed error we have, but if we are going to take someone out, we're going to subtract out their contributed error, right? So insert, increase the amount of contributed error by this, decrease by this. We know this is a positive number because we've already determined that this is the case. So our error score is still going up whenever this happens, but it's only going up by the difference between this and this, because this here is getting removed from the table temporarily, and it's going to get re-added back in when it either reaches this point or this point. Eventually, this chain of poking people out of the table will reach one of these spots, and when it does, that'll be the end of it, and we'll just put that whole thing back in wholesale. But in order for the accounting to work out, I have to subtract it here, right? Okay. So now this down here can just be a swap, which was kind of what I was hoping for it to be. Contributed error, layout.contributed error index, right? Okay, so the reason I wanted it to line up that way is so that these two look very similar. We have the thing that updates the max error score, and then we have how we put things in the table, or in this case, how we put one thing in the table and pull something else back out and continue working with the new thing, right? So these are parallel to these are parallel to these. It's the same concept in both places. We're putting things in the table. It's just in one case we're putting something in the table where there wasn't already somebody, and so that's the end of the chain, whereas here we're having to swap with someone else. So then when we do that swap with someone else, something else that happens is that first index, does that need to change? I don't think it does, because we still know that that first index was, you know, if it had been available for us to insert, we would have just inserted there. The fact that we did any swapping meant that the first index wasn't available, and if we get back around to the first index, we still got through the whole table without finding an empty slot, so that's a problem. The first time we find an empty slot, this chain is done. So whether or not it's the original thing we were trying to insert, whether or not that thing we were trying to insert now started at this first index, what's actually happening is a chain is occurring, and that chain is looking for the first empty slot. And it just happens to be that as we're looking for the first empty slot, we're swapping out who we're going to put there when we find it, if we find a better candidate for moving forward in the table, right? Okay, so these should still be happening, and now we don't need to make up for those two things at the bottom. They happen here and here now, and this part still all makes sense, so I think that's all we need to do. And let's see if that makes any difference to our result. So there we go. Our max single error score came out as a 4, 5, 5, 3, 3, 3, 3, 2, 2, 2, 4, 4, 3, 3. So it's definitely doing a little better just from that. That robinhooding just means we're not really changing anything except that when we have a run of things in the table that are all don't have any gaps between them, we're kind of sorting them in such a way that we we minimize the distance everyone in there can have to their starting point, right? It's still possible to have runs that are so long that, or slots that have so many collisions in them that you end up needing an error of 4 on a particular slot to get there, but we've basically cut in half the expected single error, maybe even more than that. Maybe we've cut it in third or something, I'm not sure. I just saw 3 over and over again for a long time. Yeah, this is way better. So that's really cool. That's robinhooding, decreasing our max single error score. You'll also notice that these aren't really any different. We're still, this is always going to be right around 66, since as soon as it finds something in that threshold, it doesn't spend very much more time trying to find something. What we could do is say, once we find a table size that works, let's spend a little bit of extra effort on that table size looking for a better index, right? So it's if we've crossed the acceptable error threshold, let's never grow this table again because we're within the acceptable threshold, but we can still try to beat it for a little while. That might be a good next move to add. So what that means is where it does the exit out of the no, this is the robinhooding. Where it does the exit out of the table is right here. So if the accumulated error reaches that, or it gets to its 100 tries on that layer, then it says, okay, let's go to finished. I want to say, let's not go to finish. Let's say, okay, we've now found the right table size. Let's not do this slot count stuff anymore, but instead let's go to a different loop that stays on the same slot stays on the same slot count, but tries for a longer period of time on that slot count to find a good table. So this is going to be go to no table growth or something like that, right? I mean, I could just actually put the code in right here that does this logic and then still go to finished afterwards if I wanted to. And I'll just leave a comment here that's like, no more table growth, keep trying to beat our best for a little bit. So how do I want to do that? So a couple ways I could actually implement this are, I could say that we only bother to do the slot count increment down here under a condition, and that condition is if our, essentially if we haven't beaten this yet. So if our best error score is greater than the acceptable error threshold, I guess it'd be greater than or equal to the acceptable error threshold, then do that. So then what I guess we could do here is say that there's like, if we've done this much, right, what we're going to do is say, okay, if we've beaten it, if we've hit our acceptable error threshold, we just want to extend our, I see what we need to do. So this is always going to happen like this. And what's actually going to happen is if we beat our acceptable error threshold for the first time, so it'd be like, if this happens, so we beat the acceptable error threshold, and first acceptable error score, then this is no longer the case, and what we do is we increment our accumulated error and our layer try count to give us an extended budget on this layer before we quit, right? So that's going to mean that up here we have a boolean to keep track of that state, and it's going to say first acceptable error score equals true, and we want to say here and here we're going to have some rule for how to extend these. So accumulated, oh, not accumulated error, that should be accumulated error threshold needs to go up, and layer try layer max number of tries needs to go up, right? So then the question is, do we increment them by themselves and just give us a double? Do we give it, like, is it a multiple factor? Maybe that's what it should be, right? It's like, just give us n extra amount. So this would be like extra effort on last layer, right? And so that can just be a number that we put in right here, extra effort on last layer. If we make it a 1, then nothing happens, and so it's just like the thing we're already running. And so if I want to give myself light optimization effort, maybe I give myself enough time to run that layer 3 steps forward, and if I want to give heavy optimization effort, maybe I go for 10, right? Let's see if we get anything cool for doing that. Alright, so now we're getting an error score of like 29, 30, 35, 40-ish. When we weren't giving ourselves extra time on that layer, what we were getting was more like, wait, the same thing? I thought that we were getting a higher error score than that. I mean, there's a 49, 40, so it's a little bit worse on average, but not that much worse, and often just as good. So I guess what this actually does is just guarantee that we get in the good range. Like this has, in this mode we have like a slightly wider range of possibilities, right? But it's like evenly distributed across them almost. And what we've done is essentially cut that in half and said when we put in a little extra effort on the last layer there, we tend to not get things in the slightly higher end of that range, right? Although even that's not totally true. Maybe, alright, well, we're not seeing any slowdown from this yet, so maybe I can afford to beef that number up a little bit. So now I'm starting to feel the slowdown. I want to make sure I'm doing what I think I'm doing. So, so if this is the first time we've beat the acceptable error threshold, that's definitely coming through correctly from the way I'm reading it. Like, the code looks right to me. It definitely looks right to me. Then accumulated error threshold goes up to give us more time on this layer, and then the layer max number of tries goes up to give us more time on this layer. I want to see if it actually gives me a super obvious improvement. And like right now, sometimes I see like 28s showing up, which I wasn't seeing so often before. And I don't see as many 40s, but I still see some. So it's like it is shifting it, but only subtly in the right direction, not like heavily. So I'm wondering how big this number has to get for us to actually feel the shift pay off at all. It might be that this isn't totally worth it. Like, we're essentially saying on the smallest layer that you found that succeeded, spend extra effort, and that smallest layer was already a hard one to optimize, so it might just be that even with extra effort you never find it. I don't know. 39, 30, 33, 33, 33, 35, 40 again, 34, 52. So how good your error turns out to be has a lot to do with which layer you stop on as well. If you stop on a layer with a smaller slot count, then you tend to get a higher error no matter how much extra effort I give you. Right here with 100 extra effort on the last layer, it's still finding an error of 52 as its best result. But that's partially because I've only given it this much extra space, right? It's got 6 extra slots of space to work in, and so what is it going to do with 100 times more effort? Isn't going to make that much of a difference. If it can't find it, it can't find it. And again, that compared to if I give it a 1, it's just not that different. Although to be honest, I don't really feel a slowdown difference, so maybe I'm just not cranking up the heat enough. Yeah, I can sort of feel the slowdown, but just barely. Let me really try to crank it up. So this 59 here is probably coming out just because it happens to have found something that works with only 3 extra slots. So whenever that happens, that we have a really small number of slots, it ends up with more error. So I was saying that I want my error threshold to be proportional to the keyword count. But that doesn't necessarily mean that I want it to be at least equal to that. Maybe what I want is more like a 2/3, right? Because I feel like it can do that, and that'll make it biased towards larger tables, obviously, but only by, well, this is actually by more than I expected it to. Okay, it's now doing a really good job of finding small errors because it's not tapping out until like it's gone that large. And so compare that to this. If I don't give it the extra effort, so if I don't give it the extra effort in this case, it's still in the 20s. So how good the error turns out to be has very much to do with what slot count it's on when it first hits that threshold. And maybe that's not a good way for this to work, I'm not sure. Like, the fact is, if it can hit that threshold, at a smaller number, then I want it, a smaller table size, that's kind of what I want it to do. Like, I want it to have a higher chance of finding the smaller table with a larger error, as long as that error is below this. Also, 66 divided by 3 would be 22. divided by 3 would be 22 times 2, 40. So 44 is my threshold, right? And it's still finding stuff a lot smaller than that, but I'm not sure I understand. Maybe it's just that in this number of tries it tends to find something at about the max. Like, this is about how much effort it needs to find the best it can find at that table size, right? And so if I wanted to do better, what I have to do is give it a larger error threshold so that it can use a smaller table, and then give it like a crazy amount of horsepower to search that final table size for small scores. Maybe that's the logic that I need to go with. Honestly, I can't feel that much of a difference. Let me give it 1,000,000. I still can't feel it. Give it 10 million. I still can't feel it. Let me give it 100 million. I still can't feel it. 999 million. Can I feel it? How come I can't feel this? It's almost as if it's not actually happening. Here's 10 billion. Extra effort on the last layer. Acceptable error threshold. I can't even let it get that big. That's as big as I can let it get, and I'm not feeling it. So something else is going wrong here, I think. Extra effort on last layer. Are you actually getting applied ever? Printf. So I give that 500. Layer max number of tries. Here I give it 100,000, and so the one thing I should maybe think about is the ratio here is like 5 to 1, and the ratio here is like 10 to 1. So maybe I need to make this ratio 5 to 1. Now when this gets multiplied in, it's going to have the same amount of effort that this has on that final layer. So it's going to do a bad job of finding the layer to work on, but once it finds a layer, it's going to put in just as much effort as this would ever put in on that particular layer to do a good job. The only difference is now this is also going to be cranking up its effort on the final layer, so it'll do an even better job potentially. But anyway, you'd think I would be able to feel that change in effort, and I just don't feel like I can. I don't feel like I can see it taking longer to do this when I multiply that in. I don't think I'm hitting my try counter, am I? I might be. I guess I could be hitting my total try counter here. I might want to just eliminate that concept from the system, I think. I'm not sure that total try count is actually helping anybody. Yeah, now it's definitely taking way longer. Definitely. So it's actually been hitting max number of tries all this time. So hard to say if that's better or not, because I didn't really get time to examine it. But let's do the following things. One, I'm going to drop you down to a 1. Max number of tries isn't going to be a thing. Instead, what I'm going to do is just say our try counter right here doesn't exist. You have to complete by actually hitting the threshold. Let's see if how that feels. It's never had trouble hitting the threshold anyway. How is that unreachable code? Are you saying there's never a time where this breaks? count. So here I increase that. I still want the logic that says if we've hit our threshold, then go to finished. Right? So this is actually not necessary, because the way this is structured in here, it increments this so that this loop we just never break out of this loop until we are done either way. And instead, this break condition here gets extended on the last layer. Alright, so this is the fast one with no extra effort on the final layer, right? It's doing the same amount of effort on the final layer as it ever did anywhere else. And so now we're getting scores of like 64, 55, whatever, and we're getting them on those slots there. So if I want to get smaller, I don't need these anymore, I don't think. If I want to get smaller tables, I have to give it more effort on every layer. But if I just wanted to take the size it ends up at and get a better error score, I should be able to do that by just cranking up the effort on the final layer. Okay, it works sometimes, but other times it still gives me a bad result. It mostly does better. Can I afford to crank it up to 1,000? Okay, so that makes the light optimization effort too costly to do. But it does kind of feel like it's paying off in terms of results. So let's just fine-tune that to be as large as it can be and hope that that's helping. It's a little too big still. Alright, I think I can stand that much slowdown. And so we're tending to get into the 40s and 30s instead of in the 50s and 60s. So that's pretty good. Now, if we try the high optimization effort with no extra effort on the last layer, it already takes a while and it ends up with table sizes of like 68 with an error score of 64. Now, we don't necessarily want such a high error score, right? The other one is actually tuned in such a way that it ends up with smaller error scores because it doesn't go for such a small table. This puts so much effort into making a small table work that it ends up finding a way to make it work, but then it can't optimize it any smaller. Let's start by seeing what happens if we give this permission to crank up the effort again on the last layer. Can it actually beat that number, or is that as good as it can do? $100 million tries max with 500 million accumulated error. Yeah, it's going to take it a while. So we can't really let it take this long. Even for an optimized build, it would be too long. But I'm curious to see if it even does any better. Because if this isn't doing any better, then the logic itself is a little bit off. We kind of want it to probably have a tighter error threshold to begin with, and then have it do less of a hard crank on the final layer, but because it's going for a slightly bigger table, it should be able to do a good job of finding a small error. Hope this is... I should have had it give me progress updates so that I would know if it's taking a reasonable amount of time or not, because now I have the problem where at any given moment I might think it's taking too long and quit it, but if I do, for all I know, it is just about done and I've just thrown away a 90% complete job. So now there's like this, well, I should have already quit. I should have quit it 5 minutes ago. No, I just might as well finish it now, and then in 5 minutes later, ah, shit, I should have quit it 5 minutes ago, right? It's never a good situation to be in. So I'm gonna cap this off at either way. I'm calling it now so that the logic is sound and there's no sunk cost fallacy later. If this doesn't finish in 2 minutes, starting now, we'll move on. So I have to fill the next 2 minutes with thoughts. I guess while we're waiting for that to run, there are things I know that I want to change over here. So 1,000 is not going to work. I think we can afford to maybe do 100. Maybe. We'll find out. Second, I think this should be forced to find a smaller error threshold. That'll force it to find a larger table size initially. And since it's so good at optimizing the table size when it has this much effort, that'll be necessary to force it to find a slightly bigger table. But then we'll know it can do at least this good. Then what we can do is say, from then on, you're just trying to beat that error threshold you've already beaten once. You're trying to beat it again, but you have a little bit of extra effort to just sit at that table size and find something even better, right? This will mean that we get slightly bigger tables out of the heavy optimization effort than we are currently. Right now, heavy optimization was kind of tuned to give us a very small table, maybe 1 or 2 extra slots, and still manage to get less than 1 error per slot. There we go. Done. Done in under 2 minutes. Good. How good did it do? Well, it managed to find an error score of 40 with a slot count of 69. That's actually better than any table we've seen so far. That's really good. So there is some payoff to the way that was structured. If we wanted a really small table with a really good error score, we could do that and we would kind of get a payoff for it. But do we want that? I don't think so. So I've just reconfigured this a little bit. Let's see how it does when I give it no extra effort, first of all, but it has to meet this threshold first. Oh shit, I didn't recompile it though, so that's just going to do the same thing we just sat through, and I don't want to sit through it again. So, if you don't mind, I'm going to shut this down. Where's my generator? There it is. Nope, stop generating. Thank you. Please rebuild, and now run. That should not take as long. It kind of looks like it's still going to take a long time. It might be that because it's got such a much tighter error threshold to meet now, and it's putting in a lot of effort at each layer trying to reach it, that what's happening is it's spending a lot more time than this does to find the error threshold it wants to start at. Maybe what we kind of want to do is tone these down a little bit at first. Like instead of being 5,000 and 500,000 and 100,000, maybe we want them to start off closer to this. Maybe not exactly like this, but maybe just give them like a 10 and a 2,000, right? Like a 10,000 and 2,000, right? And then have the multiplier here be way bigger so that it will put in a little more effort than this did to keep the table small, but not by such a huge factor. And it'll be trying to meet this more strict threshold so that its extra effort is balanced out by the fact that it has to do a better job to stop looking for a higher slot count. or for a low slot count, right? Whatever, however you want to look at that. And then once it's found a slot count that it can meet that at, it then blasts its effort up to this high only for the last round, right? This kind of feels like it's going to be another waiting for all day, and I don't want that. So, ending the process. Just to be clear, I want to make sure that that was what it was causing it. It was the smaller error threshold. Yeah. So when I cut down that error threshold, it goes right back to being able to find tables that are super duper tiny with really high error scores very quickly. And if I give it the ability to search the parameter space for like 5 minutes, which is what we just did a little while ago, it actually can get that down to 40. But I kind of want to shift the balance a little bit. So you're going to be a 10,000, 2,000 when you start, and then we want to multiply you by 50 each. Well, let's see, that multiplies by 250, so it ends up at 250,000. This is going to multiply 10 by 50 to end up at 500,000. So this is, yeah, this is still more than that. How does it do when I just do that? So now it's going for a slightly bigger table, and it's getting an error score that's really low very quickly, right? Which is pretty cool. I'll try that one more time. So yeah, this one tends to be a little more consistent since we're putting in more effort from the beginning to find good results. Sometimes it even finds smaller tables with better error scores and stuff, which is interesting. But that one was no good, even with the crank up of effort at the end. So I think we can crank the effort up higher than this at the last layer to see if it can do any better. This is supposed to be the high effort one, so I can afford for it to like take a moment, take a beat, right? Like that is kind of the amount of effort I want it to use. So let's just go one more step and just say this is nice, high effort, take a beat, and then boom. There's your table. Okay. So now we have heavy optimization doing a pretty good job. It's giving us load factors that are a little bit smaller, so it's not pulling off that like 67, 68, 69 shit that it was doing, but it's finding really good error scores for tables of that size. Now, comparing that to this, I want to make sure we're not just getting equivalent results for a much longer wait period. So there's a couple things about this one that are different. One is that the load factor tends to be a little worse, but it's kind of chaotic, right? Like, because this is a random algorithm, this always has the chance that it might find a tiny table like the high optimization one would. It just happens to be that at low effort we have more variability, but the average does appear to be a little higher. We're hitting 78s, we're hitting 79s, hitting 77s on the table size, and the error score tends to be in the 40s and 30s. If I turn on high effort, what are we getting? Take a beat. Okay, so this one managed to find a really small table, and as usual, a small table means a high error. I kind of want to do something to make that just impossible. Like, I'd rather its error never get that big. And so maybe the right call will be to force it into a smaller error threshold and then drop down its early effort a little bit. I'm not sure. If it's putting in too much effort early on, then a high error threshold is hard for it to achieve. But if I have it yeah, so this tends to be finding error scores that are a little worse still, and table sizes that are a little better, although sometimes it doesn't fit that pattern either. I want it to be a little more regular, although, I don't know. Yeah, these table sizes tend to be a little bit better on average than the other table sizes, and the error scores are a bit chaotic. Like, we are getting error scores in the 20s, the 30s, sometimes in the 50s. I would rather it never get an error score in the 50s. So what I'm going to try and do is tighten up the error threshold a little bit. I'm going to cut this down to like by a factor of like 5. So divide this by 5, we get 2. Divide 2,000 by 5. We'll divide 1,000 by divide 2,000. Divide 2,000 by 5. Divide 4,000 by 10. 400, right? Yeah. And then increase this by 5, so it'll early on not use as much effort, but on the last layer it'll use as much effort as it already is. But now it has to hit a slightly more tight error threshold to get there. So let's see if it can do that. This is a little bit more than a beat in terms of how much time it's taking. Increasing that error threshold really makes it more difficult, it seems like. But it doesn't, like, tightening the error threshold shouldn't matter so much because it's always able to find one of these fairly quickly. So like something that has a smaller error threshold than this. So like 66 times 3 is 180, 196, right? 198. And divide by 4 is roughly 200 divided by 4, so 50, right? So it shouldn't have that much trouble finding a 50 and then finishing its job. I'm not sure if I did the math here wrong or something. I had 10,000, turned it into 2. I had 2,000, turned it into 400. And I had 500, I turned it into 2,500. Seems like it shouldn't be taking any longer to me. Don't understand. Alright. I'm going to say let's forget the extra effort for now. I just want to see you actually doing the first phase correctly. And let's not put in too much effort to finding that either. Let's just do, at this point I'm dropping high effort all the way down to what the low effort is like, except that it's trying to find a higher, like a tighter threshold. Does this eventually work? As the slot count goes up, it should get easier and easier to find one. So as long as I let your slot count go up quickly, I don't know why this would take very long. But still, we're not seeing it happen. Alright, I'm going to drop this way, way down. Divide by 4 here. 1,000 divided by 4 is 250. Just find it. Just find one table with that error threshold is all I'm asking. How is this so hard? The acceptable error threshold's not that small, is it? I don't understand why it's so much harder for it to find one all of a sudden. See, that seems like a bug. That should just be finding it, like right away, because the slot count is just going to go up every single time it fails to find one. And so the slot counts should be getting huge, unless the bottleneck on speed here is turning out to be the... Where's my... Why is it ending up way over there? No, that's not the one I need. I need this right here. Unless the bottleneck on speed is building the tables itself. It's confusing. So I want to see this... something weird's going on here. Building table size D. So I'm going to build a table with that size on it, and then I'm going to report the error that I got back. Error. Here's the error score. Okay, so you found it at 90 right away. Why did you not do that when I wasn't printing things out? What changed? Did I not build? Are you still running? Shit. Okay, so that explains why I wasn't seeing any results. I still have an infinite loop in there somewhere. Okay. And adding more printing in there just caused it to happen to flush the buffer. Alright, why are you infinite looping now? I mean, besides for the fact that you don't even think I've rebuilt. Don't care about this. Error accumulation value. Error score. Layout try counter. It's not. Restore point accumulated errors greater than that, or layer try count is greater than that. Errors less than. That should be less than or equal. That's why. There we go. So that is happening immediately, as I thought it should. So now what I want to do is unroll some of the nonsense I put in here. So if you're a 2000, so you're putting in a little bit higher effort, and you're a 400, so you're putting in a little bit higher effort, and then we want you to crank it up at some point in a minute, but first I want to just see how good you do of finding small tables. Alright, so those tables are a little bigger on average than what I want you to find. So let's try to keep it under 80. Let's crank you up another notch, shall we? Alright, you're still finding tables pretty quickly. You're not crossing the 80 threshold pretty often anymore. Guess it's still happening a little bit, but not as often. Let's crank it up to this level here. I think that'll do. Alright, so you're doing a pretty good job of staying in the range of sizes that I find acceptable, but you're not getting the kind of scores that I know you can get, but that's because I haven't given you permission to let loose, crank out the big wins. So, how much heavy optimization effort can I give you? You're the heavy optimizer. Let's see, is this a beat? I want you to take like a beat, you know? That was a beat. Okay, 40 on a 72. This is kind of a small table. 31 on a 75. That's pretty good. Yeah. Now you're finding the small error. That's good. So, I think it might pay off to drop this down just a little bit more. As long as it still only takes a beat. Yeah. Okay. Yeah, that feels pretty good. Because now it has to find pretty small error scores before it'll even stop growing the table. So that just pushed the table sizes up a little bit, so I might be crossing into the 80s range again, I'm not sure. Yeah, so let's drop this back down, take a look at what table sizes we're getting, but that's getting really good error scores, so if I can just give it a tiny bit more effort up front, I think I can keep it from going into the 80s. So let's boost you by this. So it's not double, but it's halfway to double. Just don't go into the 80s very often. We'll be good. If you see the same thing multiple times in a row, that's because if I run this thing twice in the same second, my seed doesn't change, so don't concern yourself about that too much. that only counts as one thing, like one repetition of that number. Yeah, I've only seen this cross into 80 one time. There we go, twice. Jinxed it. I've only seen it cross into 80 twice. Did it again. I've only seen it cross into 80 3 times. Okay. Oh, there it did it again. Alright. Let's try a little bit more. A little bit more juice on the front end. How do you do now? Okay. Just give it one more dosage of juice on the front end. Yeah, that's really consistent. Okay. Sweet. Okay, now you're not taking a beat anymore. So let's see. Can you give me a 100? How does that look? Okay, that was good, but that wasn't a full beat. Let's see if you can take a 500. Okay, this is a little longer than a beat. That's just a tad longer than a beat. There we go. There we go. Yeah, so that's finding really good tables. That's so much fun. Okay, so we spent the time we needed to on this. We can now optimize these tables down to you know, being pretty close to, like, this for instance is using 83% of the memory it's generating for the table. That's actually a bit of a lower end of the range. We can usually get smaller tables than that from the optimized version. There we're now using 89% of our table, and then our total error score is really small, so which means that, like, our average or like our average per lookup is, like, our expected value, I guess you could say. Our expected number of iterations per lookup is 31/66, so pretty small, right? We're expecting that at least half the time we're going to get the lookup for free, and on the cases when we don't, the maximum number of iterations we're going to have to do is 2, so that's a really good table, you know? I like that. So we've done the part where we can optimize the table. I'm now going to switch this to using light optimization effort for now, so we're not going to get quite as good of a result on all runs. Sometimes we'll luck out and get pretty similar results. But the other thing we have to do now is, now that we can generate a nice optimized table, we still have to, like, we can generate the table layout, right? We need to go back down to where we were trying to generate these keyword tables in the first place and say, alright, right now what we're doing is we're reading our table and we're just printing out this, like, these metrics. And I kind of want that to be something different. So this is actually going to be our internal void debug print hash table metrics, or keyword table metrics, right? And so what that looks like is I give it a keyword layout, key layout, and an out. No, I don't give it the output file. I just give it the keyword layout. That's it. And it does all of this. And everywhere where it said fprintf standard out comma, it actually meant printf no comma, right? And so now we just have the ability to print out our tables and inspect them in a sort of debug way. But now the next big step is going to be, we need to print out our tables as C code that actually, you know, we could then include it into our Lexer and use as a lookup table, right? So far so good. We've done the layout portion and we've decreased the amount of collisions. Like, we've done our best to optimize these tables for fast lookups. Now what we want to do is we want to change gears and turn those tables into C code. No more optimization effort. It's just going to be turning those code right into C code. The only optimization we'll be doing is choosing optimal ways to generate the C code, right? Choosing optimal C code to generate from this thing. But the layout is done. We're in good shape to build these tables into C code now. All right? See y'all later. Bye-bye.